Welcome, everyone. My name is Hieu Lee. I'm a PhD student from UC Irvine, and this work is in collaboration with Salma Elmalaki and Athina Markopoulou, also from UC Irvine, and Zubair Shafiq from UC Davis. In this work, I'll introduce a framework, AutoFR, to automate the process of filter rule generation for ad blocking. Ad blockers are widely employed by millions of users worldwide. They come in various forms, such as ad blockers, like web extensions like AdBlock Plus, browsers like Brave, and standalone applications like Pi-hole. At the core of the ad blocking functionality are filter rules, string-based patterns that can match and block network requests, hide HTML elements, or stop JavaScript execution. They're often manually maintained by filter list authors who are human experts, and there are popular filter lists such as EasyList to block ads on the web. EasyList is integrated in many of the ad blocking tools. Unfortunately, these lists contain thousands and thousands of rules to create and maintain over time. In our work, we try to minimize this human effort, and we're also going to focus on the URL-based filter rules due to their popularity. So what makes filter rule generation so challenging? The first is there's an inherent trade-off between blocking ads versus avoiding breakage. In fact, it's quite easy to block ads without this trade-off. Just simply break the whole website. Unfortunately, that's not possible due to usability. So let me illustrate this trade-off with this plot. In our y-axis is how well we can block ads from 0 to 1, 1 meaning that we're able to block all ads, and our x-axis shows how well we were able to avoid breakage, 1 meaning there's no breakage. So for a site with no rules applied, it behaves normally. There's no ads blocked, and there's no breakage as well. However, once we apply a filter rule, it may block all ads, but it may also cause some legitimate content to be blocked as well. Ideally, what we want is this top right corner here, where we're able to block all ads with minimal or no breakage. So this is our ideal region. However, we also consider the right side of the plot to be an acceptable region because filter rules can block some ads, and as long as they cause minimal breakage, that's okay. And filter list authors can deal with this trade-off by using different types of rules here. For example, they prefer using the ELCD form of the rule because they can use one rule to block an entire domain that is involved in serving ads. But if that overblocks and causes breakage to the user, they can use more finer grained rules, like the ones with paths. However, that makes it easier to be evaded. The second challenge is in the high human effort in creating and maintaining filter rules. Let me illustrate this by walking you through a typical workflow of a filter list author. For example, we have a filter list author, and she's tasked with creating rules for a given site. In this example, we're going to assume that there are no existing effective filter rules. So she's not going to know exactly what to do right away. What she can do is look at all the outgoing network requests from the site by using developer tools, and she's going to select a URL to block. Here she can use her domain knowledge or keywords like ads or bidding. And she can apply it on the site, refresh it, and manually visually inspect the impact of this filter rule, of the URL. And she's going to consider this trade-off again, and she's going to want something that's on this top right corner. If it is effective, she now has to figure out, well, what filter rule can I use to block this URL? So there's different types as mentioned before, and she's probably going to use the more preferred one first, the ELCD one. She's going to have to once again apply it on the site, refresh the page, and then visually inspect it again. As we can see here, there's and she'll do this iteratively over and over until she has a final set of rules to block the majority of ads with minimal breakage. As we can see here, there's high human effort, especially within these areas where she has to consider all the potential outgoing network requests, all the possible filter rules, and all the manual visual inspection. As we can see, this iterative trial and error process is naturally lends itself to using reinforcement learning, which I'll go into later. So AutoFR aims to address these two particular challenges. So far, I've discussed the challenges to this problem. For the rest of this talk, I'll talk about our formulation using reinforcement learning, our implementation of our framework, and then we'll end with some evaluation and future directions. Our contributions lie within the formulation, which enables us to go from a human process to an automated one, and also our implementation, which goes beyond a naive one that may take hours per site, and we're able to reduce that down to a few minutes per site, and that allows AutoFR to be a practical tool. So within this vast literature of reinforcement learning, we choose to formulate the problem using multi-arm bandits for two main reasons. We considered the effect of a filter rule, for example, how it blocks ads, how it avoids breakage, as independent from each other. So if you do apply two or more filter rules together, their effects are additive at best. We also considered that there are site dynamics, meaning that when you visit a site, there may be different text, images, ads served to the user. So it's not enough to test a filter rule once on the site. This rule has to be effective across multiple sites, multiple visits. And the rest of the formulation, I'm going to explain it using standard reinforcement learning. Here, we can now replace a filter list author with what we call an agent. It's a smart entity that is now tasked with learning the best filter rules for this given site, and it must do so within a given time limit. To do this, it follows a policy. Here in our paper, we use a standard upper confidence bound policy that enables the agent to balance this trade-off between exploring unknown filter rules that may be effective versus exploiting filter rules that are already known to be effective. And so our potential filter rules are now our action space, which is all the set of rules that the agent needs to explore. And every time we select a filter rule to test, that's our action. To derive our action space, we can simply take all the outgoing network requests and then generate the URL-based filter rules as shown here. We're also going to exploit an inherent hierarchical structure within filter rules. For example, if we look at doubleclick.net, it's an ELCD form. However, it also has its FQDN forms as well, and there's a more specific relationship, as we noted with the dash edges. The intuition here is that we want to try the coarser grained filter rule first. If it causes too much breakage, then we want to try the more specific ones. This allows us to reduce the number of actions that the agent needs to explore. Next, when a filter rule is applied to the site, we consider this our environment. And we can now replace the manual visual inspection with a reward. This is a number that measures the effectiveness of how a filter rule blocks ads versus avoiding breakage. And this number allows us to consider this trade-off automatically. Let me show you how we can do this. We're now going to represent how a site is with the visual components, such as the counters of ads, counters of images, and text. And there's various ways that we can actually get these numbers. For ads, for example, we can use a web extension like Ad Highlighter that detects ads using ad choice logos. For images and text, we can simply write custom JavaScript to count the image and text nodes. And we can use these counters now to compare the difference between how a site normally behaves with when it behaves when rules are applied to it. And so using these counters once again, we are going to define our reward function. And there are various ways that we can do this. Let me explain one that we found to be effective. Our reward for a filter rule takes in three parameters. CA hat denotes how well we block ads from 0 to 1. And this is simply the difference between the counters of how the site normally behaves, the counters of ads for how a site normally behaves versus when a filter rule is applied, and this is our y-axis. B simply denotes the difference between how images and text change when a filter rule is applied. And therefore, 1 minus B is avoiding breakage, and that's our x-axis. W is a threshold that is provided by the user to separate the region between what is unacceptable to the user compared to what is acceptable to the user. So here, our case A for a reward says that this filter rule did not help at blocking ads at all. So we give it a reward of -1, we don't care. Case B shows that this rule was able to block some ads, but falls within the unacceptable region to the user. And giving a reward of 0 helps guide our algorithm to say, okay, we need to explore the more specific rules now. Our KC shows that this filter rule is a good rule. It is able to block some ads, and it falls within the acceptable region for the user. And due to time, I'll leave the rest of the formulation to the paper. Next, I'll explain our implementation of our framework. And I'll focus on one particular real-world bottleneck, which is waiting for the site to load all its legitimate content and ads. And when we apply reinforcement learning in a real-world setting, this takes hundreds to thousands of visits to the site in order for the algorithm to converge, and this may take hours. And to address this particular bottleneck, I'm going to introduce the concept of site snapshots. It's basically a graph representation of how a site is loaded and is able to connect, for example, how a JavaScript can create an HTML DOM element and how that element can perhaps initiate network requests. And here I'm showing a very simple example of a site. However, within its raw format, we actually don't know whether the image is visible to the user or if the iframe is an ad. So we simply have to annotate this graph now. For example, using custom JavaScript. Here I denote the image in blue as visible to the user, and we're going to use add highlighter to annotate that the iframe is an ad. So now using this graph, we can apply our filter rule in a post-processing manner. For example, if we block JavaScript B, we're able to infer that we blocked the ad, and so that's a good rule. However, if the rule blocks JavaScript A, we can infer that it blocked ads but also caused some legitimate content to be blocked as well. And we're going to use this concept now and collect 10 site snapshots by visiting the site 10 times without any rules applied. We're going to annotate the graph and save them locally as graph.ml files, and then reuse them. So what we've done is actually replace the potential hundreds to thousands of visits to the site down to a fixed number of site snapshots. In our work, we recommend using 10 to capture the site dynamics. And so for each time we apply a filter rule, what we're going to do is simply randomly select a site snapshot and then apply it in a post-processing manner. And this enables AutoFR to be efficient and scalable. Next, let's discuss our evaluation. For efficiency, if we take a toy example of one site with only 10 rules to explore and we have to visit the site 1,000 times, we estimate that this would take around 13 hours. When we employ AutoFR on the top 5,000 sites in the wild, we find that AutoFR has an average efficiency of 1.6 minutes. In fact, if we looked at all the runtime of the sites, we find that 80% of sites takes a minute or less. Now we can look at our performance as well on the top 5K by using our trade-off plots here again. Here we use W as 0.9 to represent a filter list author who wants effective rules but can tolerate a little bit of breakage. And here for AutoFR, it generates rules that has 86% of sites within the top 5K within the acceptable region. We do the same for EasyList, and we find that it has 87% of sites within the acceptable region. And so we see that AutoFR is able to generate rules that are very comparable to the state-of-the-art filter lists. However, we are able to do it in an automated fashion. Next, we look at rule granularity. We find that AutoFR is able to generate rules with similar type distribution as EasyList, and this is crucial for the robustness of the rules, as ESLD ones are harder to evade. In our paper, we conducted extensive evaluation. Due to time, I'm only able to talk about the bolded ones. Please look at our paper for more information. We envision AutoFR to be the template of future filter rule generation research. For example, our framework is tunable. People can explore different rewards. The action space can be extended to create rules to hide ads, and it can go beyond ads, such as creating rules that can block tracking or for other platforms like mobile devices. In short, AutoFR is a framework and tool that can generate URL-based filter rules to block ads while avoiding visual breakage automatically. Our paper and artifacts are publicly available. Please use and extend it. Thank you.